Hi. Today we're going to be talking about the mean value theorem, which is the back half of lesson 4-1. Here we go. So in class, we would start off with the examples of discovering the mean value theorem. If you haven't done those examples yet, I would highly recommend you try them out now. It helps motivate what's going on. But for a video lesson, I'm going to do this in the reverse order. It makes more sense to me. So, mean value theorem says that if f is continuous on the closed interval, and we should note that this means including endpoints, and differentiable on the open interval, meaning f prime exists and is a nice number, then there is some number c in the open interval. Again, that means not including endpoints. That's a common source of error. Such that f prime equals this average rate of change expression. So this is a secant slope, an average rate of change. This is a tangent slope, an instantaneous rate of change. I_roc equals A_roc. That's the big idea of the mean value theorem. I_roc equals A_roc. There'll be a place where the average rate of change, this secant slope, will match the instantaneous rate of change, this tangent slope. So if the tangent slope's in blue, we're talking about that line. If the secant slope's in pink, we're talking about this line. Or at least thereabouts. Informally, the mean value theorem says that if we have the right conditions of continuity and differentiability, there's at least one tangent line parallel to the secant line. The instantaneous rate of change will equal the average rate of change at least once. That's a really big idea. We have to find a way of checking these conditions. And that's what these examples are about. So we're going to kind of see what happens. Here we have my secant slope. And to find the slope that's parallel to it, I would take a copy of that slope, a copy of that line, and we move it up until about here, where it's tangent to the curve. So again, what we're talking about is that that is a secant line. And because this function met those conditions, we have one tangent line that's parallel to the secant line. So far, so good. This function was continuous and it was differentiable. No sharp turns, no vertical tangents, and everything was just beautiful. Another one. So there's my secant line. And if we made one copy, we could find a point of tangency around there. And another copy would fit nicely tangent there. So this again, in orange. So that was the secant slope, the secant line, I'm sorry. And we actually found two tangent lines. So the mean value theorem allows you to have more than one possibilities. We're just saying we guarantee you that at least once. At least once. Another example. Our secant line would be here. Some students don't like calling this a secant line because it hits the function in more than two places. That's okay. This is still definitely a secant line. So when we try to copy it, these are not tangent lines. A common student mistake is to call this a tangent line. It doesn't look like a tangent line. A tangent line, the idea is we're matching the behavior close to the point. There's not one point, I have 2 points, and I'm not matching the behavior at either point. You might be tempted to say that is a tangent line, but the astute student, a student might say there's no tangent line. And the reason we were prevented from drawing that was the sharp turn. And now we might start to see why differentiability is necessary. This would be a differentiability issue between A and B. In example 13, we can draw what might be called a secant line between A and B, but in some cases we would not really want to say that's a secant line. So I'm going to emphasize that it's not really a secant line. It doesn't really represent the average rate of the change over the region, and that's because of this vertical asymptote. The vertical asymptote is causing us a lot of trouble. If we try to copy this line, we would see that nowhere do we really get a matching behavior. So we see that that asymptote has prevented us from having a tangent line. And again, it's due to that same vertical asymptote that stopped us from having a secant line, really. So a discontinuity within the interval caused us to not be differentiable, caused us to lose that tangent line we had in those first two examples. Now here in this example, we can't even get started. There's nowhere for us to even draw our secant line attached to. So this one, we have no secant line, which means we will have no tangent line to even try to be parallel to. So here we weren't differentiable within A and B, we weren't continuous within A and B. Here we're not continuous at A. We're continuous everywhere else, we're differentiable everywhere else, but we're not continuous at an endpoint, and that caused a serious issue. Finally, here to here, and we try to draw, and right where we get to where we would call it a tangent line, we find that we are not able to really call this a tangent line for the same reason we talked about in example 12. So there's just no tangent line, and that's due to the hole. It's even worse in example 12. Example 12, that's a sharp turn. This example, it really looks like it wants to be a tangent line, but we're missing a point. So there's no point of tangency. I can hit the curve multiple times if I really wanted to, but not having a point of tangency caused me some trouble. So for 16, 17, 18, now we're going to show you, so these functions all meet the conditions. So what kind of things can we get? So we want to find that value, an x value. We can emphasize that this is an x value. Wouldn't be a bad idea. There is a number c. We're talking about an x value where I rock equals a rock. So we're looking for those numbers in these examples. Let's begin with this tangent line. So with that tangent line, we're going to do the same strategy where we copy it and look for that point of tangency right there. That's right where this graph behaves just like that line. And I would say the C value is around 3. Now don't get nervous. If this were a test question, we would accept things like 3.1. We would accept things like 2.9. We would not accept things like 4. We would not accept things like 2. Especially not accept things like 2 because that's the endpoint. Here, that looks like a fairly good secant line. I'm going to try for it one little bit better. Go for the center of the point. Now, we're looking for points of tangency. We have one right there. We have one right there. And we have one right here, probably. However, we're looking between the interval from 2 to 5. So we won't really count that. So the third tangent line, not an interval. The interval we're interested in is 2 to 5. So this tangent line looks, I don't know, about 2.7. Again, we're just estimating. And this tangent line, I don't know, 4.3, 4.5. Doesn't really matter. Okay. One more. So there's our secant line. Here's one tangent line. Maybe I'll move it a little lower. And we look for another tangent line. And you might be able to see that if you adjust right, you get this tangent line here. Now, this tangent line up here hits the points in 2 locations, and they're both points of tangency. It's very confusing for beginning students who are under the impression that a tangent line can only hit the graph once. No. The tangent line can hit the graph multiple times. It's very confusing. Most of those other times are not tangencies. This is. A point of tangency for a tangent line is a place where we just barely hit the graph, where the behavior locally matches the slope of the tangent line. If that's all very confusing, it's not super necessary to understand it all crystal clearly right now. The idea is that these two are points of tangency. We have 2 tangent lines. This tangent line intersects the graph twice, and both of these match the conditions. So, of being a point of tangency, because the slope at that point matches the slope of this line. So, we'll call that 2.5. We'll call that 3.5. And we will call this 4.5, just to keep it all even. Okay, so when we have a graph that's continuous and differentiable, we're fine. Some people object, this guy's not differentiable at the sharp turn. It doesn't matter. We are continuous and differentiable on the open interval. We don't worry about being differentiable at the endpoint. Oh, I suppose I should notice this one down here would also intersect the graph and be tangent around there. But just like, for example, 17, this point of tangency is not in the interval. Okay? So we're going to make sure we throw out ones that aren't in the interval. Throw out solutions that aren't in the interval. That are not in the interval. Wow. So here we go. What will a problem actually look like on the test? Something closer to this. So whenever you see the mean value theorem, we should think to ourselves, oh, I want to find out where A rock equals I rock. I think I said that in the reverse order. So we're going to look at the tangent line, making sense with the secant line. Our first goal of business will be to calculate A rock. In case you forgot, it's still that same formula. F of B minus F of A over B minus A. The average slope, the average rate of change. F of 6 minus F of 3 all over 6 minus 3. So A rock F of 6 will be the point 3 minus 1 or 2, the y value 2. F of 3 will be 3 minus 2 or 1. So the average rate of change is just going to be 1/3. Okay? That's part 1. Part 2, I rock, is F prime. Now, before you go and use the quotient rule here, be very careful to just calmly rewrite the function without a variable in the denominator. The quotient rule is a highly inefficient way of taking this derivative. This is much easier. The derivative of 3 is 0. Negative 1 times negative 6 is positive 6. X, negative 1 minus 1, negative 2. It'll be useful to rewrite this without the negative exponent, so we will. If you're wondering how I decide whether it's useful or not, whenever we're using the derivative, which we will be doing a lot in this chapter, it'll be useful to rewrite the derivative without negative exponents. So now we use the idea that I want A rock to equal I rock. Okay, we're focusing on this equation. So we want 6 over x squared to equal 1/3. I cross multiply. 18 equals x squared. X will equal positive root 18 and negative root 18. And now, whenever you get your answers, you should consider, are both of these in the interval? This one is pretty clearly not in the interval. It's negative. What happened? It's negative. That interval is only positive numbers. This root is in the interval. I know that for 2 reasons. Reason number 1, we were guaranteed to have an answer because this function is continuous on this interval. It is not continuous at 0, but 0 is not in this interval, and it's differentiable on this interval. This derivative is not differentiable at 0, but it's not in this interval. Easy peasy. I also know that square root of 18 equals 3 root 6. And a similar argument as in the last video could show us that 3 times root 6 is less than 6 and bigger than 3. It should be pretty clear that's going to be bigger than 3. It's 3 times a positive number greater than 1, but finding that out would be a lot like the last example. All right, that's it for this lesson. You should now be able to complete the entirety of 4-1's homework. Good luck. Ask me any questions. Bye for now.